Hello everyone, this is Junpeng Wang. I'm a research scientist from VIS Research. On behalf of all my co-authors, I will present our work, Visual Analytics for RNN-Based Deep Reinforcement Learning. I will explain three topics in this talk. First, what is deep reinforcement learning and why it is challenging? Second, I will cover some key visual designs that we introduced in this work. Lastly, I will briefly discuss how our work is useful and contributing to the deep learning field. Reinforcement learning is to train an agent to accomplish certain tasks in a predefined environment. It always contains two components, the agent to be trained and the environment to be interacted with. Taking the Atari Pong game as an example, the agent controls the pedal on the right through different actions, such as moving the pedal up or down. The environment is the game itself, which provides feedback to the agent with a reward and the next game state. This interaction loop continues for numerous iterations, generating a sequence of actions, states, and rewards. The unique part of deep reinforcement learning is that it trains the agent through deep neural networks. Since the settings here involve temporal information, RNN is a straightforward choice. Let's just take three consecutive game steps here to illustrate how the model works. First, a CNN is used to extract the essential state information from each game screen. The information includes all types of static information, such as the position of the ball and the pedal. Next, the RNN takes the extracted information and the previous RNN hidden and cell state as input, and generates a new hidden and cell state. We assume the RNN here is an LSTM. HX and CX are used to represent the hidden and cell state, respectively. The same process applies to the second and third game step as well. The RNN states here encode the dynamic information, such as the direction and the speed of the ball. At any step, the agent needs to know what action to take. It is decided by a function taking the hidden state as input. There are three types of reinforcement learning to implement this function f, but their details are out of the scope of this paper. Instead, what have been really captured by the RNN internal states are the focus of this paper. Analyzing RNN-based deep reinforcement learning is challenging. First, the game episode to be analyzed is lengthy with thousands of steps. Second, the dimensionality of the RNN states is usually high, making it hard to interpret what each dimension is responsible for. Third, there is a gap between the machine understandable numerical values and the human interpretable semantics. For example, tracking the hidden state values across steps will not tell us what has been memorized by the agent. We have to interpret the agent in a more intuitive manner. Given those challenges, let's now take a look at our new visual designs and interactions. For the challenge of long game episode, we address it through two techniques. First, we explore the long episode through overview plus details. The overview presents a curve reflecting the value of a statistic across steps. It provides informative hints for users to dive into individual steps. The detail part replaces the game at those steps to show the details. Second, we introduce a variance map to visually aggregate a sequence of game screens. Each pixel of the variance map reflects the variance of the corresponding pixels of the game screens. Extending this to all pixels, we get the variance map, which presents the sequence of screens through a single static image. From the example here, we know the ball is traveling along the path of A to B to C. The second challenge is the high dimensionality of the RNN internal states. We also use two techniques to address it. The first one is dimensionality reduction. Let's take the cell state as an example. Assume the dimensionality of those RNN cells is 256, and the current episode has 1000 steps. So the cell state from all steps is a matrix of 1000 by 256. Through t-SNE, we project those 256D vectors as 2D points. Next, we use a threshold to connect consecutive steps. The red bar here is the threshold. The 2D points that have a distance to his previous point smaller than this threshold are connected into segments. In this example, the threshold is 8, and the thousands of points become 21 segments. Clicking individual segment, we can check the corresponding steps variance map. For example, the currently selected segment shows the earlier stage of the breakout game, where the agent uses the side walls to bounce the ball, and the ball travels along longer paths. The segment on the right shows the later stage, where the agent keeps moving the paddle between point A and B to catch the ball, and the ball always directly hit bricks around point C. The traveling paths here are shorter, and the agent is more efficient. Our second technique in handling the high-dimensional RNN cells is dimension sorting through different metrics. Each dimension is a time series curve with 1000 steps, and we have 256 such curves. We can sort these curves by different metrics. For example, let's simply computing the mean of individual dimension across the 1000 steps and sort those 250 mean values decreasingly. The dimension with the largest mean value in the Pong game is shown in purple here. The periodic pattern is very obvious in later stages. Through some examination, we found this dimension is a step counter, which increases a fixed amount every step, and it gets resets every game cycle. The highlighted red portion is a game cycle, and the corresponding VIS map is shown here. The video clip replays the game and pauses at point A, B, and C. Point A is where the ball appears in the scene, point B is when the ball hits the floor, and point C is where the opponent misses the ball. Through the synchronized views, we found point B is where the step counter gets reset. You may wonder what happened for those earlier abnormal patterns. They are the cases where the agent failed to catch the ball. It's good to see this step counter dimension, but is this a common thing of the model, or it is just a cherry-picked result? To verify this, we applied the same dimension sorting to other games and found similar step counters. Here are the step counters for another 3 games. For Atari Sequest, the counter also gets reset every life cycle. For Breakout and Space Invader, there is no resetting point. Our guess is that the game screens of those 2 games keep changing as the bricks or invaders keep being destroyed. There's no reappeared game scene, as a result there is no resetting point. You may wonder why simply sorting by mean could identify the step counter dimensions. The reason is that the cell state values of an RNN are not bounded. If one dimension value keeps increasing, it will easily distinguish itself from other dimensions. Let's look at another example. The model's output at a step is a probability distribution of all actions. We can compute the entropy of this distribution to derive the confidence level of the agent. This figure shows the agent is very uncertain about what action to take, and the action distribution here has a large entropy. In contrast, in the red figure, the agent is very confident, and the entropy is small. Connecting the entropy at individual steps forms an entropy curve, and we can compute the correlation between different RN hidden states with this curve. Sorting the RN states with their correlation value, we identify the orange curve here from the breakout game. The corresponding hidden state dimension actually reflects the ball's moving direction. Let's zoom into a small segment to explore the details. From point A to B, the ball flies toward the paddle, and the value of this dimension is around 0. From B to A, the ball bounces up, and the value of this dimension is around 1. From A to C, the value becomes small again as the ball goes towards the paddle. From C to D, the hidden state's value increases back. In short, small value indicates the ball is going down, whereas large values indicate the ball is going up. Let me explain how this dimension can reflect the ball's direction. After the agent is well trained, he learns that he needs to carefully choose actions only when the ball is coming towards the paddle. As a result, actions from those steps are usually confident, and the entropy of those action distributions is small. In contrast, when the ball is going away from the paddle, the agent knows that he is safe and there is no difference in taking different actions, so the entropy of action distributions at these steps is large. Since this hidden state dimension correlates with the entropy value, it can easily reflect the ball's moving direction. For the third challenge of better interpreting the less intuitive numerical values, we borrowed the existing perturbation-based methods to interactively generate salience maps for user-interested game steps and RN dimensions. In general, the RN function takes the game states st and the hidden state from the last step to generate the new hidden state. If we modify the game state st here, the resulting new hidden state will also be changed. In detail, we introduce a mask at one location of the input screen. the difference between the output hidden states hxt and hxt prime is recorded for the corresponding masked region. Extending this process across all regions of the screen, we generate a salience map. Overlaying this map on top of the original screen, we extract the regions that the hidden state focused on. Moreover, we can improve the granularity of the mask to make the salience map more precise. For example, this is a real salience map. It shows the corresponding hidden state dimension focuses on the ball at this step. Extending the same computation to a sequence of steps, we generate a salience map video from which we know the current hidden state dimension tracks the ball. Let me give another example with the Atari Sequest game. First, by sorting the RN hidden state cells, we identify two interesting hidden state dimensions, and they also show similar behaviors. Second, as you can see here, both show significant oscillation at the end of each life cycle, and these oscillation regions help us locate the important game steps for analysis. Third, zooming into the user-interested dimensions and the user-interested steps, we replay the game. From the synchronized wheels, we found the oscillation corresponds to the flickering of the oxygen bar. In this game, the agent needs to learn that he cannot stay in the sea for too long, or he will die due to the lack of oxygen. The flickering of the oxygen bar warns the agent. Lastly, by replaying the salience map video, we can effectively verify that this dimension is indeed focused on the flickering of the oxygen bar. Please check our paper for more interesting cases. To the last point of this talk, I want to briefly summarize how our findings could be useful. First, these findings help to interpret the agent. For example, we can clearly see that the agent is aware of the ball's moving direction. Second, our finding can be used to diagnose the failure cases. The step counter dimension is a good scenario, where the abnormal behaviors of the RN cells could trigger the process of debugging. Third, we're currently exploring how to use the findings to improve the deep reinforcement learning models. By sorting the RNN cells by their variance, we found dimensions with very small variance across steps. These cells are candidate for us to prune the model and reduce the RN size. To conclude my talk, we introduce a visual analytics system to explore and interpret RN-based deep reinforcement learning models. From the exploration with the system, we provide actionable insight into the interpretation, diagnosis, and even the improvement of the reinforcement learning models. Thank you for listening.